Hello everyone and welcome back to the continuation of chapter 2 from the famous book of Introduction or a First Course in the Finite Element Method by Daryl L. Logan, the 6th edition. And today we're going to finish chapter 2, which talks about stiffness matrix introduction, spring elements, and so on. So last time we talked about basically a simplified spring question or example, and today we're going to continue by trying to connect all the missing dots by a bigger example. Before I start, I had a nice comment from a subscriber, Donald Khani, who correctly mentioned that step 2 and step 3 from the multi-step finite element procedure mentioned in the first lecture, which is being linked above, were missing. And those include the choice of displacement and stress-strain relationships. The idea why those are missing is because for a spring, what is our mission objective basically? Our mission objective is to find a matrix, or vector F, that equals a stiffness matrix K multiplied by the movement or displacement matrix. Let me call it D for now. And truth to be said, for a spring, this is ready because according to physics, a spring force F equals K multiplied by X. So there is no need to assume any displacement or stress forces relationships. You have it directly. Now, in the future, we will be doing step 2 and 3 for more intricate elements, but still a huge thank you and shout out to him because, I really enjoy those discussions because they not only help me, but help the viewer too. Anyway, with that being said, I have one example and then I want to introduce something called the energy approach, just a small introduction to make you a little bit intrigued to read the book. I really highly recommend you get yourself the book, A First Course in the Finite Element Method by Daryl L. Logan. This is a really amazing book. Some people ask me like, okay, if I want to go deeper, what should I do? There is a deeper book by Bathe, and he's a German. His name is Klaus-Jürgen Bathe. He was, I think, at MIT, and I think it's called Finite Element Procedures. And this book is the cryptic brother of Daryl L. Logan. So I suggest Bathe for anybody who has finished a first course in the finite element method. If you finish this with me, then I can suggest to you that you check out Finite Element Procedures by Klaus-Jürgen Bathe. This is like the more detailed and deep dive book compared to Daryl L. Logan, and this is really research stuff. And it's really cool if you have finished this and you want to go deeper for your PhD. But if you are still not knowing what finite element is, then I highly recommend this book, I highly recommend that you buy it and support, of course, the author of that book. Anyway, I am going to solve problem 217 from that book, which basically tells you that there is a 5-spring assemblage. You can say node number 1, node number 2, node number 3, and node number 4, and there are 5 springs. And of course, he gave you the K factors of each spring in newtons per millimeter. Here I need to mention that there is a unit thing that you need to keep an eye on that. So right, what does he want from me? Well, he wants me to find the displacements and the reactions. I will find more than this. You will see by the end of this video, this is really cool. So notice here, node 1 represents the left support. Node 2 represents the entire bar. Why? Because it's a rigid bar, meaning if any point on the bar moves, the entire bar moves. So node 2 is basically everywhere on the rigid bar. Like this is node 2, and this is node 2, this is node 2, and this is node 2. They are connected by a rigid link, something that exists in Autologous Robot. Similarly, node 3 is basically those all, because if one of them moves, everyone will move because it's a rigid bar. And 4 is basically the full support. Okay, so with that being said, let's take a look. Now, assembling the stiffness matrix. There are 2 warnings. The first warning is units, but here it's not really dangerous. And the second warning is to keep an eye on the connectivity. So for the first element, remember the stiffness matrix Fi and Fj equals K minus K minus K and K for the movement at I and the movement at J, where I and J are the nodes. So if you have from node 1 to node 2, then you would have F1, F2, and so on. So let's take a look here. Element number 1. Now, please notice that this was explained in detail in the previous video that I will link above, so take a look on that. Node element number 1. You see that element number 1 connects node number 1 with node number 2. So, of course, the stiffness matrix for element number 1, small k, superscript 1 is the k minus kk, the shenanigans we know, and you can see that k is 500 here. Now, for element 2, what do you think the stiffness matrix is? Well, element number 2 connects 2 with 3 and has a stiffness of 300. So I'm expecting 300 minus 300 minus 300. 300, lo and behold, it is. Element number 3. Strangely, element number 3 also connects node 2 with node 3. So you can almost see that you could just sum them up and reproduce one big element instead. But I will not do that. So element number 3 is going to have the same stiffness matrix, 300s everywhere. Element number 4 has a stiffness of 405, so you will see 400s everywhere and 500s everywhere in element 2, 3, or 4 and 5. Now this is so far simple. I hope that you're getting bored, because if you're not getting bored, then I suggest that you check out the previous lecture. If you're getting bored, then you are perfectly fine. With that being said, let's start our global stiffness matrix. Now wait a minute, you would say. This is in the local direction. You should not be able to assemble it in the global direction. But remember that for this chapter, you can see that if the global x-axis goes to the right, it coincides, it's parallel with all the local axes of all the elements, and that's why there is no transformation matrix needed. You will soon see what I mean by this. So let's try do it by hand here, and later I will show you the slides. So this here, let me just put some numbers here. This is node 1, node 2, 3, and 4, or U1, U2, U3, and U4. This is 1, 2, 3, and 4. So 1 with 1, right? We're talking about 1 with 1. Which elements have 1 with 1? The only element that has 1 with 1 is this. So this is 500 here. What about 1 horizontal with 2 vertical? And by the way, notice that I opened a matrix of 4 by 4 because the degrees of freedom are 4. Because I have 4 nodes, so I have 4 possible movements. What about degree of freedom 1 with degree of freedom 2? This is only here because the only 1 with 2 exists in K1, so this is negative 500. 1 with 3 doesn't exist because take a look. This is node 1, this is node 3. There is no direct connection between them, so that's 0. Similarly, 0 for 1 to 4 because 1 and 4 do not see each other. What about 2 with 2? 2 with 2 exists here. That's your 2 with 2, and also exists here and exists here. This is your 2 with 2 everywhere. How do I know those exist here? Look, look, look. This is row labeled 2, and this is a column labeled 2. Notice that this element is from 2 to 3, so you have 2, 3 here, and 2, 3 here. Notice that element 3 is 2 to 3, so you have 2 here, 3 here, 2 here, 3 here. This is 3 to 4, so you have 3 here, 4 here, and 3 here, 4 here. This is 2 to 4, so you have 2 here and 4 here, as well as 2 here and 4 here. What do you want? You want 2 with 2. 2 with 2 exists almost everywhere. It exists at element 1, element 2, element 3, and element 5. Summing those together, you would have 1,500 if my calculation is correct. Of course, I will open the slide in a moment. What about 2 with 3? This doesn't have 2 with 3. This has 2 with 3 and it's negative 300. This has 2 with 3 and is negative 300. And that's it. So negative 600, I think. I'm really sure. What about 2 with 4? 2 with 4 exists only here. And it's negative 400. I'm doing this very quickly, so I might mess it up. I will see the slide in a moment to make sure. 3 with 3 exists here. That's a 300, 300, and 400. And that's it. So 3 with 3 is 300 plus 300 plus 400 should be 1,000. I'm doing a very quick calculation again. 3 with 4 exists where it exists here. 3 with 4 is negative 400. And 4 with 4 exists, I think, in 2 elements, right? Yes, it exists here, 400, and 400 should be 800. And the rest is symmetric. So let's take a look if I got it right. So wait, 500, that's correct. You can see the circles helping you. Negative 500, 0, because it doesn't exist, 0, negative 1500, negative 600, that's something we've done just now, negative 400, and so on. You can see each element being highlighted. Of course, here the rest is filled by symmetry. Okay, cool. Now the system of equations we have here is now F capital, which is your global force, equals the stiffness matrix K multiplied by the deflection matrix or movement matrix U. And how do I solve that? Remember, what is our objective here? He wants me to find the deflections in the nodes as well as the reaction forces. Now, some of those U's are known and some of those F's are known. What are the U's I know? Well, the U's I know are U1 equals 0 because it's fixed, and U4 equals 0 because it's fixed. One would think, but doctor, this seems to be fixed. No, this is a ruler. It can move in the horizontal axis. This is also not fixed because it's a ruler that can move in the horizontal axis. Yes, this point restrains movement in the vertical axis, but our degree of freedom is in the horizontal direction, so that's why this restraint in the vertical doesn't help at all. What about the forces? F1x is unknown. F1x is the external force applied on 1. That should be the reaction. F2x is known. F2x is known because there is no external force being applied on node number 2, so 0. F3x is known because there is 1,000 Newton applied on node number 3. And F4x is unknown because it's the reaction of the wall. Now, with that being said, you can solve this. How can you solve that? Well, you have zeros here, which means you can destroy or eliminate the first column because the first degree of freedom is fixed. And you can destroy the fourth column because the fourth row because the fourth row is fixed. Similarly, fourth column, fourth row, what remains is basically the system of equations. And you can solve that. And if you solve this, you find the displacements which are in millimeters. And now, of course, this is the displacements. How can you find the forces? To find the forces, well, take a look. You have force 1x. Let's expand the matrix. Force 1x equals 500 multiplied by 0, because u1x is 0, minus 500 multiplied by u2x, which you know, plus 0 multiplied by u3x, which you know, plus 0 multiplied by 0, because u4x is 0. And you can see this happening here in real time. F1x being calculated, F4x being calculated. And you can see that this is the reaction force here and the reaction force here. Also check reaction plus action equals 0, equilibrium. This is reaction of wall number 1, this left side. This is reaction of wall number 4, this right side, and this 1000 is your force. And you can see you have equilibrium. Because the reaction at 1 is negative 263, so it goes to the left, 263. And the reaction on 4 is 736, so it goes to the left. Of course, if you add them all together, you get 0. Now the question is, that I can read your mind, I think. The question is, for reaction at 1, we understand. It's 263. But at 4, Dr. CE just drew one arrow, 736. But wait, this arrow is basically distributed on 2 elements. So what is the share of each element from that reaction? I'm glad you asked this, dear hypothetical viewer, and although my example has finished, I'm going to dive deeper. So now I'll go to the beauty of statics. I want to find the internal spring forces. So each spring has a force. How do I find that? Well, remember that each spring has a stiffness matrix. If you multiply the stiffness matrix by the U matrix, or vector, then you can find the internal forces. And that's what I'm doing here, which is this. Notice that you are allowed to use the global U's because there is no transformation. So, element number 1 connects node 1 with 2. So force 1 small and force 2 small. What does it mean? F1, 1x. It means F small means the local force. This one is the element number. This one is the node number. And this x is the direction. And of course, this will give you negative and positive. This means that your element looks like this. This is element number 1 connecting node number 1 with node number 2. At node number 1, it witnesses a tension or a force going to the left side, -1,5, and on the right side, it sees the opposite. Notice that this element is under tension. Although you have a negative sign here, it is still under tension. You have a negative sign because the finite element method gives you the forces in the local direction. And the local direction is to the right. If you have left, then you have negative. Similarly, you can find the force on each and every node. And that's something that is straightforward. You can just multiply the vectors and matrices. Now, are those in compression or tension? Well, I just spoiled this for you, but let's wait for the final slide. Let's continue with this. Element 4 and element 5 are being shown. Everything seems to be perfect. Now, those are the internal forces, but do they add up? Now, let's reveal this. So let's take a look. For the general structure, I found F1x and F4x, and I dubbed them the reactions. And this is in equilibrium because the 1000 goes to the left, and those two dudes are 1000 to the this 1000 goes to the right, and those two dudes are 1000 to the left. Let's go to the elements. Element number 1 had negative here, so left. This was negative, so it's left. And positive here, so right, which means it's in tension and it's in equilibrium. Element 2 had negative 236, so left, and positive 236 to right. You can see it's in tension and it's in equilibrium. Perfect. You go to element 3, same thing. You had two forces. This means in tension and it's in equilibrium. You go to element 4. Element 4 was in compression. Let me show you here. Element 4 had F3x positive to the right and F4x negative. So if I apply them here, that's your joint number 3, and it was positive, so it was going to the right, and joint number 4 was negative, so it goes to the left. This is compression. Element number 5 had joint number 2, I guess, going positive, so to the right, and joint 4, I think, going to the left. So compression. Now the structure is in equilibrium. The elements are in equilibrium. So are we done? No, we're not done. We want to check the nodes. If you go to the nodes, I think there is a arrow here. For some reason, I forgot to animate it. Let's go to node number 1. This force is F1x1. This is the force from spring number 1. And this is the external force from the reaction. You can see that this is equilibrium, so perfect. Now let's go to node number 2. Node number 2 is really peculiar. Node number 2, let me just remind you, this is node number 2, right? Node number 2 has 1, 2, 3, 4 elements connected to them. So let's take a look on node number 4. Now, element number 1 was in tension, so of course it pulls on node number 2. Element number 2 was in tension, so it pulls on node number 2. Element number 3 was in tension, so it pulls on node number 2. Element 4, I think element 5, was in compression, so it pushes onto node 2. If you sum those forces up, it's 0. If you go to node 3, well, you can see on node 3 that, let me just check what was connecting node 3, just to check. Okay, 2 and 3 and 4. So you can see on node number 3, element number 2 is under tension, so it pulls on the node. Element number 3 is under tension, so it pulls on the node. Element number 4 is under compression, so it pushes on the node. Now, if you sum those 3 up, you think that's not in equilibrium. It is in equilibrium because the summation of the forces here and the 1000 external force is 0, so it's in equilibrium. Finally, the final node is node number 4, and I asked the question before that this reaction, how is it distributed on the elements? Now, first of all, those are the actions of the elements: compression, compression, and of course it's in equilibrium. But just in case if you're wondering, this 736, what are the reactions? The reactions could be decomposed into 500 something here and 200 something here, exactly as you can see here, because if you decompose the 736 to 500 here, 200 here, you still maintain the equilibrium. So yeah, that's everything I wanted to talk about in this example. Before I finish, I want to show you the. So I hope that it makes sense now and that we understand the basic principles of finite element method. This final slides with this equilibrium and the beauty of statics unfolding might need you to sit down, and I suggest you sit down with a piece of paper and try to do it yourself to understand those beautiful static realizations. Okay, now, energy approaches, right? First of all, I will not be covering it right now because it might be overpowered for this section. You should read section 2.6, page 55. Basically, what is the idea of an energy approach? A structure would have the tendency to move as long as it has not reached the minimum potential energy. Let's say that for a structure, the minimum potential energy is 9,000 joules. If a structure is at a power level over 9,000, as Vegeta says, yes, I'm throwing in a DBZ reference, say 9,120, then it can, look, the minimum potential energy is 9,000, and it is at 9,120, you know that it can still go down to 9,000, which means you have an excess of 120 joules, which is released in form of deformation. So when do you stop deforming? When do you reach static equilibrium and stop any movement? You reach static equilibrium and stop any movement when you reach the minimum potential energy. That's the idea. So basically, a quick glimpse about this is you can find the potential energy of the spring movement and of the external forces, and then try to minimize this by saying d pi over du, for example, equals 0. And it's really cool. And it satisfies the potential net inside you. It's basically like the Kaioken. This is just a slight introduction about that, just to explain to you how the idea works, because you want to find the point of minimum potential energy to stop moving, and that's basically it. So yeah, that's everything I wanted to talk about. I hope that you enjoyed the video. Of course, if you have enjoyed the video, then please like, share, comment, and subscribe, especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video.